All right. Welcome back to this intro to power electronics, DC to DC converters course. This week we're going over isolated topologies, efficiency, and regulation. Just as a reminder of, what we're doing here. So we're basing our discussions on this DC to DC Book of Knowledge by Steve Roberts. This is available for free by Recom or whatever, however you pronounce that company's name. And then we're going to be planning to meet once a week. I know for some of you that might have missed last week's meeting, we were originally planning to meet twice a week, but we're doing that once now. And we're doing this on Mondays from 5 to 6 p.m. Pacific time. And we're not going to be meeting on July 13th. And I've also updated the schedule. So here's our schedule that we're going to be working off of this quarter. I have cut some topics out, but, or actually, sorry, I haven't really cut any topics out, but I've reduced, um, I guess, the amount of meetings. I've basically cut it in half since we're no longer meeting on Wednesday. I had to, condense some of the chapters a little bit more, but we're covering everything that I think is appropriate for this class anyway. But yeah, so here's the schedule, and feel free to look at that at some other time if you're interested. I put together a little knowledge check for the material from last week. I'm not gonna read through all of this, but if you feel comfortable, right, looking at these questions and being able to answer them, I think you do relatively well in an interview situation, right? I mean, I know these are questions that are just like going over things that we covered last week, but these are very typical of things that you might see in an interview. Like I've heard a lot of these questions actually asked during the interview process, right? I've been on the other side of the table of an interview, and I've also, asked some of these myself. So uh, I would recommend going through them, making sure that you understand the answers, and go from there. So at the end of last week, we were talking about a project to kind of convey or go over, the concepts that we're learning. And I came up with this, thanks to Lucas, right? We kind of discussed continuing to use the Arduino Mega, which is a little board that is touched in EE151, the freshman intro lab to electrical engineering. And then we kind of just never used the Arduino Mega ever again. So in this little project, we're talking about how we can create a power source for the Arduino Mega as opposed to, just powering it from our laptop, which is typically done throughout the entire quarter. And part of this project, so this project has two stages. The first stage is using a buck converter to take a voltage from a solar panel and step it down to 6 volts, and then using a linear regulator to then take that 6 volts and take it down to 5 volts to feed into the Arduino Mega. And so I've given some suggestions on kind of how to get started, right? So we got to figure out how much current that the Arduino Mega needs, first of all. And then we'll want to design the buck converter for about 10 watts of output power, just, in case we want to power anything else like an LED or a motor, right? In addition to the Arduino Mega. And, maybe later on in the quarter, we'll define more projects that branch off of this buck stage so that we can have more power or use up more of that power. And I've defined some little goals, right? So the first goal is to have over 90% efficiency, which is not uncommon for, these 10-watt buck converters. In fact, you could probably get up to 96% if you designed it really well. And then we also want to keep it relatively small. So maybe 10 by 10 millimeters, right, or 100 square millimeters. And the last thing we want to do is make sure that you can actually buy whatever integrated circuit buck converter that the little PWM regulator chip that you find. You want to make sure that you can actually purchase that on some kind of distributor so that if you choose to do so, you can actually go and build this project physically instead of just simulating it. And so I've given this solar panel from Amazon. I actually have one of these in my home lab. So, um, I'll probably build up this little project too and kind of test it along with you guys. And, um, it's a relatively cheap solar panel. I think it's like 20 bucks. So if you wanted to get one yourself and kind of build up your own home lab, you could pretty easily do so. And honestly, if you're looking for funding, I'm happy to sponsor a little um, your project within reason, right? And so I'll go over the solution, or at least a solution, next week at the start of these classes, and then I've also given some other recommendations on more reading to get started on this if you're interested in doing this project. So the first reference is this basic calculation of a buck converter power stage. So this is a really great resource for learning more, right, in detail about the buck converter itself, and then also how to choose the various components within the buck converter, right? It's a relatively short article, right? It's only about 8 pages, so definitely um, a reasonable task for completing in a week, I'd say. And of course, if you have questions, feel free to reach out. But that's a good place to get started. And then there's also this ADI Power Studio Designer, which I haven't used all that much, but I came across it the other day, and it's kind of nice to um, give you a first cut at a design, right? So you can specify your input voltage, right? Maybe, um, well, if we just go and look at this solar panel, it kind of tells you different specifications for it, right? So it's got a peak voltage of 18 volts, and I know it's nominally 12 volts, it says here. Um, so we could just say maybe we've got a minimum input voltage of maybe 12 or maybe 10, and then nominal of 12, and then maximum of 18. And then maybe we're designing for 5 volts, or so we're designing for for 6 volts, right? Based on that project. And then we wanted 10 watts. So if we take 10 by 6, we figure that the current is about 1.67 uh, amps. And then you can just go ahead and generate a design. And so it'll do a bunch of stuff in the back end, and it'll come up with a bunch of designs for you. And then at which point you should take a look at the specific chip that it's using, right? And make sure that you've got your efficiency requirement that I've specified, and then also the size requirement. So you can see this one is already too big, and then this one doesn't quite have enough efficiency, but it's very small, right? And this one is right where we kind of want it. So the first thing, that you'd want to go and do is kind of make sure that you could maybe purchase this specific device on Mauser or DigiKey or wherever. And in this case, we can. So it's cool. So anyways, this is a good tool to kind of get you started, just making little designs, and it's worthy of a first little project, I'd say, in power electronics. For reference, the buck converter is kind of like the hello world of power electronics. Everyone seems to start with the buck converter. And yeah, So it looks like, yeah, I just put together a slide to quickly review the buck converter. Um, as we had talked about last week, it's a non-isolated converter, and it can only step this input voltage down, right? So we have the switching node or the switch node here, and when we turn the switch node on, or when we turn the switch on, the switch node goes up to Vin, and then when we turn it off, it is basically tied to ground through this lower switch, right? This lower diode. It's basically shorted to ground there, minus whatever forward voltage drop is in that diode. And so the idea here is we have our switching node, and then we take it through an LC filter, right? This is a low pass filter. We're getting rid of those high frequency transitions to create a nice and smooth DC output voltage. And as we had talked about a little bit last week, depending on how long this switch is turned on for, right, or the duty cycle, right, because we're controlling the switch with a periodic waveform. So if we turn it on for longer, we can effectively increase this output voltage. And again, this is can only step the voltage down. So the output voltage can never be higher than the input, right? If we just turn this switch on indefinitely, well, this inductor is going to turn into a short. The capacitor is then going to see the voltage that's being applied, right? Eventually, going to charge up to that, which is just in fact the input voltage minus whatever drop there is in the switch and whatever drop there is in this inductor, right? So this output voltage again can never be greater than our input voltage. And yeah, that's just a review of how the buck converter works in preparation for your little project if you guys choose to do that. All right. And so unless there are any questions on any of that, we can jump into this week's material. And again, please feel free to stop me at any point if you guys have any questions. We can talk through them. So isolated topologies, again, review from last week. We have an isolated topology will have separate current paths, right? There's a path for current on this primary side of the transformer. There's a transformer here with a primary winding and a secondary winding, right? And the secondary winding is then connected to the output, which is just modeled as a resistor here. This resistor, right, is going to be drawing some amount of current. And this is an isolated topology because there is a separate path for the input current and for the output current. And again, if we look at the buck converter, the input current is not isolated from the output current. They have the exact same return path or this ground node here, right? Everything is going back to ground. But here we effectively have two different grounds. Hence, this is isolated. So there are five main isolated DC to DC converter topologies, and they are the flyback, forward, push-pull, half bridge, and full bridge. And they operate very similar to the non-isolated topologies in that they're just sending packets of energy from the input to the output. But so these isolated topologies tend to be a little bit less efficient than the non-isolated topologies just because we have a transformer. And so this transformer has, a primary winding, a secondary winding, and it's got some core loss, right? This is not a perfect conversion of voltage to from this end to that end. There's also some additional copper loss, right, in the inductance of these primary and secondary windings, right? These are effectively inductors, which are not, you know, perfect wires, right? They have some resistance. Um, but yeah. So getting into the different types of these isolated converters, we first have the flyback converter. And so flybacks are probably the most widespread um, isolated converter. You'll find them all over the place. Um, and so they store energy in the transformer itself, right? So here I've got the transformer, I've got a switch connected to the primary winding of the transformer. And all I have really on this primary side is the source and then the transformer primary inductance and then the switch. Right, so it's a very simple topology, and that's most likely why you see it all over the place is because it's got such a low component count, um, and it can achieve this isolation very easily. But then going on to secondary side, we have a diode, and then we just have a filter capacitor, and then this resistor to model the load, basically. So this is our output voltage between these two nodes here. And so the way that this works is the switch S1 turns on, right? So we've effectively created a short from here to here. Then current is going to flow through the primary winding of the transformer, right? This is T1. And so it's going to create a little magnetic field through that inductance, and the magnetic field is going to couple onto the secondary winding, and it's going to then cause some amount of current to flow. And so one thing to note here is this dot convention of these transformers, because that's one thing that people often forget. And honestly, I had to look up just to make sure that I had it correct. The general idea is when current goes into the primary dot, then it's going to exit the secondary dot, and vice versa. So in this case, when S1 is turned on, we're actually leaving, right? This is exiting the primary dot, which means that it'll want to enter the secondary dot. And it can't do that because in that case, this diode will be reverse biased and it's going to block the current from flowing into this secondary winding here, right? So when I turn the switch on, current will flow through the primary winding of the inductor, create a magnetic field coupling onto the secondary, but the secondary cannot conduct current this way. And what effectively is happening, like I said here in this top statement, is that the energy is just being stored in this transformer, right? Because it's not flowing directly to the output, right, as soon as the switch is charging up the magnetic field of the transformer here, the primary winding. Um, it's only when we turn the switch off, right? So if we open up this switch, then, well, the inductance will want to keep the current flowing. So it's actually going to kind of send the current back into the source there. But then once we turn this off, it'll allow the secondary winding to send current out of the dot through that diode there, right? Because the polarity effectively reverses, right? Instead of current going this way, coming out of the primary dot, we're now going into the primary dot. So then we're going to go out of the secondary dot and flow into the capacitor and then into the load as well. Um, right, so I know that's probably a lot to take in right now, um, but that's just kind of a very high level of how this flyback converter works, and I hope that makes sense. Um, Obviously, if you're, I think in interviews they don't necessarily expect you to be able to um, explain all the different isolated topologies because they can get a little bit more complicated, right? And especially if you're applying for an entry level position, this can be beyond what is expected for a lot of entry level people. But if you understand it now, more power to you because That's very good. All right, so going in a little bit deeper into this flyback converter. So the switch, and this is just me kind of poking at the book a little bit. So they put these waveforms in, which are somewhat easy to follow, but I don't necessarily agree with this 2V in, um, which is this is showing the peak voltage across S1, and it's actually going to depend more on the transformer turns ratio because this will then cause the output voltage to be reflected back into the input, right? And so this switch will actually see, sure, it'll see V in, but it's also going to see the voltage across this primary winding here. And so that's actually going to be depending on the turns ratio, right? This reflected output voltage is going to be the output voltage scaled up by the turns ratio itself, right? So for example, if I had a 10 to 1 turns ratio and and my output voltage is, maybe 5 volts, then this 5 volts is going to appear over here as 5 times 10, right? So it's going to appear as 50 volts across this primary winding, just due to the turns ratio of the transformer and just how transformers operate in general. I know you guys haven't had too much experience working with transformers, but it's very simple, speaking in terms of voltage ratios at least. And so again, that's just me kind of poking at the book, but this switch will need to be able to handle a pretty significant amount of voltage. And that's, I guess, just kind of getting into one thing that you might want to be careful with when you're picking out switches. And so these switches, again, these are typically MOSFETs, and MOSFETs will usually have a drain to source voltage rating, which you'll want to make sure that is above whatever stress, right, this switch is going to see. So you'll need to be cognizant of what that is exactly. Um, it's not necessarily going to be twice VN, but it'll certainly be more than VN. So just something to note. And so when the switch turns off, as we had talked about before, this diode is going to turn on, right? When the switch was on, the diode was actually blocking just due to the dot convention of these transformers. But then when it turns off, the diode conducts and it allows current to then flow to the output, right? So we're sending energy or little packets of energy to the output, and this energy is coming from the stored energy in the magnetic field of the transformer there. And the diode is called a peak rectifier because it's kind of clamping the magnetic discharge voltage, right? It's kind of only allowing that much voltage, that peak voltage to be seen there. Um, and so just looking at the different switch waveforms, we can see when S1 is on, right, the diode is off, just as we had talked about. But then also there's no voltage across the diode, so that's kind of important to note. But then as we turn it off or we open it, the diode is going to then conduct, right? So it turns on and it captures this peak value of the switch voltage, right? Hence the peak rectification. So it's conducting so long as that switch voltage sees the peak value, and it's sending that magnetic discharge energy to um, the output. All right. So now getting into forward converters, right? So we looked at these flyback converters, and it's storing energy in the transformer, right? We turn on the switch, store some energy, and then we turn off the switch and we discharge that energy to the output in the flyback. These forward converters don't store energy in the transformer. We're just kind of continuously sending it, from the input to the output. And just kind of taking a look at the topology, it's a little bit more complex than the flyback, but they tend to be more efficient. Um, and we'll kind of get into why that is a little bit later, but just know that, they tend to be more efficient. So when we turn this switch on, just like in the forward converter, we cause the current to flow through the inductance of this primary transformer. And again, we have this dot convention, but this primary dot is actually um, coupled with both this winding and this winding. So that's just something to keep in mind with this forward converter. So as we have current going into this dot, when the switch is on, D3, right, the current's going to come out of this dot, but it can't. So D3 is blocking, and then we come out of this dot, this third dot here, and we can actually flow through this diode, right? And so when switch one is on, we have D1 conducting, right? So this is turned on. This is effectively charging up the output, right? We're sending energy over to the output. And then as we turn switch one off, we now have the polarity reversed at this primary winding. So current is going to be coming out of the primary dot, which means it's going to go into this dot. And D3 is then going to conduct. And D3 has a very special purpose. So it's actually quickly demagnetizing the transformer core. So we didn't have this action right in the flyback converter. It's a very different mechanism of transferring power. But so we're resetting the transformer core, um, and then current since current is now coming out of the primary dot, it's also going into this this like output dot, right? So it's going into there, right? So D1 is actually blocking, but there's actually still energy, right? Just due to the magnetic field. So we can actually send current out this way, and it's going to go through D2, right? Because this diode is kind of acting as a short circuit for the current, right? It's gonna prefer to go through this diode compared to the capacitor right away. So it's gonna come through the diode. It's gonna go through this inductance, and again, it's going to continue charging up the output voltage. Um, it's kind of at a slower rate, I believe. But in any case, right, it's a very different operating principle than the flyback converter, where when we turn the switch on, it charges up a magnetic field, and it's kind of being blocked from even getting to the output, right? Looking back here, as S1 is on, right, this we can't even send energy to the output until we turn S1 off. Whereas here, we can kind of just continuously send energy over so long as there's energy in the magnetic field of that primary inductor in the first place, right? So we obviously have to turn the switch on first in order to start sending energy. Because if this is just left open, then there's not really any current. This diode is just continuously blocking this auxiliary winding from even building up any energy there. Um, so yeah, this is a forward converter. There's also an active clamp variation of the forward converter. So here we have a sort of passive reset mechanism with this diode, right? We can't control exactly when this diode conducts, but it kind of works, right? So it's usually good enough. Um, but here we have an actual switch, right? This controllable switch that allows us to go and actually reset the transformer after it's been magnetized by S1 being turned on. We can quickly demagnetize it there and have more control over that. And this also has the benefit of reducing the voltage stress on this S1, right? Because before, when we had this setup, um, S1 actually sees the input voltage and whatever output voltage is being reflected back via the turns ratio of this transformer. But now it just sees VN because we can turn the switch on to quickly demagnetize the core here. And so the most voltage that this S1 will ever see will be VN there. All right. Yeah, I'm hoping this doesn't run too long. This is a pretty loaded discussion on these isolated topologies. We're just trying to get a high level view of all of them though, right? Um, so next up we have the push-pull converter, and I've never actually seen one of these in practice, but it's might be something worth knowing at some point, maybe, who knows? But these have a split winding transformer, right? So we have a primary winding, which is actually cut in the middle here, basically. Right, we kind of tap off of it here to get into our input voltage source. And the same thing happens on the secondary side, but the tap here is actually going to the reference potential of our output. So, and the general principle is when S1 turns on, then we're magnetizing, right, this top primary inductance, and then the current is then going to be pulled through D1 to the output there. And then likewise, if we instead have S2 turned on, then we're going to be magnetizing this lower inductance of that split transformer. And then current is then going to be pulled to the output via this second diode D2. So it's very similar, I think, to the forward converter operation in the sense that we're not really storing energy, right? It's just kind of continuously, pushing and pulling energy through these transformers. But that's a push-pull converter. And then we have the half bridge converter. So if you've ever seen a bridge circuit, just for example, maybe we have two parallel paths here, right? And I'm just drawing these as resistors for now. So we have two parallel paths, and then if we have something connecting them in the middle here, this is kind of what we call a bridge circuit, just in electronics in general. So this is called a half bridge, primarily because we have these two switches that, form a series path between this top node and the bottom node. And then it kind of has this tap, the center tap going through the transformer primary winding there. So that's a half bridge. Oh yeah, so I talk about the branches here. So Q2 to Q1, that forms a branch. Um, and the way that we operate this is only one of these switches will be turned on right at any given time. Because again, if we turn both of them on, right, and this is actually some kind of input voltage source that's kind of tied between these two nodes usually. Not sure why they cut that out. If we turn both of these switches on, we've effectively created a short, right? We're shorting out our voltage source, and that's going to cause high currents, and things will break. So only one of these switches should be turned on at a time, and so that has the effect of connecting this primary winding node to either the input source or ground, right? And we can use that to then send energy over, right? Because this transformer can't really send DC energy. We actually need some kind of switching mechanism to send energy across. And unfortunately, they didn't have any good um, waveforms, like the characteristic waveforms that we saw in a lot of the other examples. But this is more of a advanced topic, I'd say, the half bridge and the full bridge, at least. So we don't need to talk about them in too much detail, but maybe for a later day. So here we have the full bridge, and it's a full bridge because it's an actual bridge. We have this parallel path here, or we have these two parallel branches, right? Q2 and Q1, and then we're being bridged via this transformer to this other path, this other branch with Q3 and Q4. Um, and so just like the half bridge, we never want a, you know, this series path from the input source to ground to be conducting at the same time because then we'll cause a short. So how we operate this instead is we cause the diagonal switches to be conducting at the same time, right? So Q3 and Q1 will be on, and then they'll turn off, and then Q2 and Q4 will turn on. And so this has the benefit of removing high ripple current from these capacitors here that were in the half bridge. So these capacitors aren't necessarily filter capacitors where, we have our LC filter here to remove the high frequency switching components of the switch node. These capacitors are actually in the power path, right? So power is kind of flowing through either this switch or this capacitor in order to get to the output, or this switch or this capacitor. So these capacitors will see relatively high ripple current. Um, and to give you some context, right, we haven't really talked about this all too much, but capacitors have some amount of resistance. And if you have current with a relatively high RMS value, then you're going to actually have significant power being dissipated in those capacitors. And then those capacitors will break down just like anything else that has high enough power, enough to like melt the part a little bit, right? So the full bridge has the benefit of, removing the need to worry about high ripple current through the capacitors. We just throw in switches there instead, which tend to have a much higher tolerance for current in general, right, than capacitors. All right. So unless there are any questions on that, I know it's a lot. It's a lot even for me. I'll admit I haven't seen most of those in practice. I've only really seen the flyback and forward, but we can move on to efficiency, which is a little bit of an easier topic here. So electronic devices are parasitic. They're not these perfect components, right? We have our capacitor, inductor, diode, and then a switch or field effect transistor, which we've got there. They have everything has resistance, first of all. I mean, everything, and then everything has capacitance. Um, right, whenever you have two plates of metal, you've effectively created capacitance, and everything has, or at least all of these basic devices have at least two terminals, right? And with two terminals, you certainly have capacitance, and every physical object has some amount of resistance. And so you can very easily see that these things, these like perfect components are not anything near perfect, right? They have all kinds of problems with them. But fortunately, we can compensate for all of these imperfections as long as we have good characterization of the part itself. So a good data sheet will actually tell you things about all these different parasitics that, come into play. And so there's something to note that, switching converter efficiency mostly depends on these parasitic values. When we were looking at the linear regulator, all of the current, just to draw it again. So um, we had our linear regulator, right, and it has some kind of pass transistor, and it's just got some kind of voltage divider network going into like an op amp with a reference. I mean, that's all to say that everything in the path to the output has to squeeze through our little pass transistor here. And I apologize that this is a terrible drawing, but this pass transistor has some amount of resistance, and it's a significant amount of resistance too, right? But all of the current is going through that resistance, and so we, tend to have terrible efficiencies in these linear regulators. But there are a lot more um, sources of power loss for these switching regulators, right? We still have parasitic resistance, and now we have switches which don't actually turn on and off instantaneously. It takes time. And during these switch transitions, we can actually have a case where power is being dissipated just due to overlap between current and voltage, right? Because power is the product of current and voltage. So if we have those kind of overlaps, then you're going to have power being dissipated, and those can actually add up quite a bit, which is why you don't see, really, really fast switching regulators like PWM regulators for the buck converter, for example, right? You won't really see anything above maybe 1 megahertz, because at that point the switching loss starts to kind of take over and dominate to the point where it's not even really all that effective to be switching that fast. Um, and of course, just like the linear regulator, there's the need for bias current to power up all the auxiliary circuitry. Um, and then we also have magnetic components, um, which we, obviously didn't have in the linear regulator. We've now got inductors and transformers, and these things have, different losses associated with them as well. So we've got a bunch more sources of power loss, but somehow we're still able to come out on top pretty significantly, actually, right? You can see these efficiencies for these really basic topologies. They're all easily over 70%, where the best possible linear regulator that, we could really make is probably 60% efficient there. Um, yeah, that's kind of all I had to say about efficiency. And so jumping into regulation, so most of these basic switching regulators use pulse width modulation, and we looked a little bit at that in EE151, but just as a refresher, so we have pulses going at a fixed frequency and we're literally modulating the width of the pulse, right? So for example, 50% duty cycle, we're on for half the time and we're off for half the time. And if we crank that up to 75% duty cycle, we're on for three-quarters of the time and off for a quarter of the time there. It's a very simple concept. Um, and, we're usually using this to control the size of these energy packets. Right? So if I'm on longer, obviously I'm sending more energy from the input to the output. It's very simple a concept. But on the concept of regulation, there are two main control methods here that are kind of built on top of this pulse width modulation, or I guess they're used to implement pulse width modulation. So first off, we have voltage mode control, which we take a look at our scaled output voltage, just as we did with the linear regulator, right? We scale it down and we feed it into an error amplifier, which compares it to whatever reference voltage we're looking at. And then based on that amplified error, we will then, use that signal to turn our switch on or off, right? Again, this PWM signal is what's driving the switches on and off. Um, so in this example, right, when this VF is above our oscillator frequency, we're going to turn this signal on, right? Um, or I guess, let me see. Yeah, yeah. So it's going to start off. Did I read that right? Sorry, hang on. So if the amplified error is 5, then the PWM is going to be on while that's less than 5. Yeah, okay. So typically we have, within the controller circuitry, we have a reference. Well, so not necessarily a reference, right? This is kind of like an oscillator, we call it, but it is basically it's just being compared to our amplified error, and then based on where we are in this, sawtooth waveform, it's going to set the output PWM on or off. Um, so here you can imagine, I guess, if this is actually true, then the PWM is going to be on for a very small amount of time, right? Maybe this sawtooth waveform is counting up to 100 or something, right? So it's going to be on for maybe 5 ticks, and then it's going to turn off for the rest of the 95. And so in a case like that, right, we're probably really close to our reference voltage. Um, and so we're only sending a very little bit of energy to the output there. And that's kind of like the basic concept of this voltage mode control here. And so here we have current mode control, and this is a little bit more tricky, but it also has a voltage loop, right? So we're still comparing that output voltage amplified, or the output voltage scaled down compared to the reference and then amplified. And we still have our little oscillator, but now our oscillator is just sending really quick pulses here to set this PWM flip-flop. Um, and I guess we haven't really talked all that much about flip-flops, at least in 151, but it's a relatively simple concept. There is a set and a reset input, and then there's an output Q, right? So SR, this is an SR flip-flop. When S is a logic high signal, such as the start of this oscillator pulse, the output is going to be high, right? So this output's going to start off high, and then it's going to only go low once this reset input is high. So at some point, right, we have our reset go high, and this will occur when VF is above our sensed current there, right? So we have, in addition to our um, amplified little error signal here, we also have a current sense path here where we actually just have a little shunt resistor to absorb some of the output current, and we actually measure the voltage across that, and we send that into this comparator here, right? And once VF comes above that sensed current, then we trigger our flip-flop to reset. Um, and so current mode control is a little bit faster than only having voltage mode control, right? Because here we're just looking at the output voltage, but here we're actually looking at the switch current, which is, being adjusted every single time the PWM signal is going off, right? So this is occurring at a much faster rate compared to the output voltage, which is just kind of slowly reacting to the change in the load current. Um, but then one thing you do trade is a little bit of efficiency just due to this sense resistor. But nowadays, I think, maybe 80–90% of controllers will operate in current mode control, just due to the need for fast regulation and um, just because, it's still relatively cheap to implement this, right? It doesn't take all that much. Um, and it looks like that's all I've have for this week. Unless there are any questions, I'm happy to take them now. All right, I'm gonna stop the recording here real quick.